Szanowni Państwo, niezmiernie się cieszymy, że możemy przywitać Was w kolejnym programie Winnovators. Ten rok szkolny kończymy 2 spotkaniami kosmicznymi. Pierwsze, niezwykle dla nas ekscytujące już dzisiaj. Jak Państwo widzą, swoją czołówkę zmieniamy, bo zmienia się otaczające nas życie. Jak z Pawłem zaczynaliśmy Winnovators, to tym bodźcem, tym motorem, który nas popchnął do zapraszania na takich ciekawych gości, był COVID i wtedy w życiu byśmy sobie nie pomyśleli, że tuż za naszą granicą będzie się odbywała wojna, która też jest tragicznym wydarzeniem i też zmienia świat, ale tym bardziej uważamy, trzeba się spotykać z mądrzejszymi ludźmi niż my jesteśmy, rozmawiać z nimi i słuchać, czerpać ile się da. I naszymi dzisiejszymi świetnymi gośćmi są Mark. He tried to teach me how to pronounce his name, but I think I wouldn't say it properly. So Mark McCaughrean, it was close. I oczywiście Artur Chmielewski, nasza polsko-amerykańska największa gwiazda kosmosu świecąca. Bardzo się cieszymy, że już za chwilę będziecie Państwo mogli wysłuchać. Dzisiaj technologia jest trochę przeciwko nam. Artur mówił, że ma problemy z prądem, co zapewne teraz Państwo widzą, że połączenie Artura nie jest bardzo stabilne, ale mamy nadzieję, że zaraz do nas wróci. Paweł?
Myślę, że mamy dzisiaj tak ciekawe spotkanie, że oddajmy głos jak najszybciej naszemu gościowi.
Dobrze, spróbujmy. Artur się znowu połączył. Artur, podłoga jest twoja, jak mówią na Dolnym Śląsku. Hello? Artur, do you hear us?
Yes, I do now, but it's really choppy. Okay. I really apologize. In California, maybe you heard we have these wildfires, and so one of them started because a lightning struck a generator, electrical generator, and the company had to pay, I don't know, $100 billion. So now they turn off the electricity whenever we see there's a chance of lightning. So I apologize, you may lose me. You know, there are some good things about living in California, but there are some that are not so great.
Okay, so the floor is yours. You are waiting. One
Okay.
thing, Mark, you have to insert one more time your presentation because it disappeared. I don't know.
So in the meantime, can I give a intro?
Yeah,
for Mark?
It's yours time. We are disappearing with Pavel.
Well, so here's the executive summary for those who are very busy of introduction for Mark. Mark is the smartest guy that I have ever known, okay, in the entire world. And I work for NASA, so I know some smart guys, and okay. So that's the English short version. In Polish, to jest jeden z najmądrzejszych ludzi na świecie. Okay, do I need to say more? Well, I do. I worked with Mark on a mission that was flying this thing. Mark, do you remember the name of this fun object?
67P Czurumów Gerstmienka.
Very good. Okay, this was an exciting mission, and Mark was one of the principal scientists there. He would work between all the scientists working on the mission and then explain their science to the general public and sometimes to us engineers. So that was his job. And I think that, Mark, you're an interdisciplinary scientist on James Webb Telescope. This is an amazingly difficult job. So these folks who are called IDSs, short, interdisciplinary scientists, That's what they do. They basically, there's a person who's looking at extrasolar planets. There's a person who's looking at IR signals in different wavelengths. And there are people who are responsible for various scientific endeavors. And Mark connects them, okay? So there's in these what we call silos, but Mark connects them and allows them to talk to each other and decide what are the priority observations. And he also takes that information and explains it to the ESA and NASA management and to the general public. A very difficult job. Did I describe it at some level reasonably, Mark?
As always, Artur, as always, yes, you do a brilliant job. Thank you.
Well, the floor is yours then.
Well, thank you very much. Thanks very much, Artur. Thanks very much to everybody for inviting me this evening to talk about what is one of the most amazing space missions that has been developed ever. And it's actually taken about half of the lifetime that human beings have been in space, and we've had machines in space to develop it. I mean, it started in the 1980s, so almost 40 years ago now. And we're very close to the point where we will actually get scientific data in the next few weeks. So it's a very exciting time to be talking to you about this particular mission. But let's just start by reminding you that the European Space Agency, working with NASA and working with other agencies around the world, has many more missions. So Artur just mentioned, for example, the Rosetta mission, which was this fantastic mission to a comet between 2004 and 2016. Something that I think captured the imagination of the public around the world. So not just science, but also the engagement with space that people feel. And I think JWST will have that for different reasons. We're not going to the places in the way that Rosetta did, but we're able to see them from large distances all the way back to the beginning of time, as I'll explain. But you can see we have a whole range of missions which have finished operating like Rosetta, which are currently operating. Just tomorrow, we have our Bepi-Colombo mission, which will be making its second close flyby at the planet Mercury, just 200 kilometers above the surface. It needs to use these flybys to get itself into orbit. That happens in 2025, but we'll get a good glimpse tomorrow with the cameras of what Mercury looks like. And we also have missions which are for astronomy, looking out into the universe, so places we can't go, far away from the sun. We've had many missions in the past, the ones at the bottom. We're operating many missions today, including Gaia, which is surveying our Milky Way galaxy and has released the most precise catalogue ever of the positions and motions of all of the stars in our galaxy just last week. And then new missions coming along for dark energy and for X-ray astronomy and for gravitational waves. So a huge portfolio. But I'm going to talk about just one, and that's the James Webb Space Telescope. And this project was originated in the United States by NASA as a successor to the Hubble Space Telescope, essentially. And in fact, the first meetings that took place on this mission happened even before Hubble was flown. So the book you see on the left-hand side there was published in 1989, almost a year before Hubble was actually launched in 1990. And we realized at that point that what Hubble could do was going to be amazing, and it has been, but that for certain scientific questions, we needed something else. We needed a bigger telescope. We needed a telescope that was cold and sensitive at infrared wavelengths. And that's the machine you see in the right-hand side. That's a picture taken last November at the European Space Agency's launch site in French Guiana, Kourou. The telescope's all folded up here and ready to be put on the launcher. As you'll see later on, that then has to unfold like a kind of reverse origami to be able to then be a full telescope. And I'll describe how that works a bit later on. So that's that journey. But of course, human journey in space or looking out at the universe is much longer. For the hundreds of thousands of years that we've been a species, we've been looking out into the night sky. And until, in fact, in recent history, where we polluted most of the night sky with our streetlights, we were able to see the Milky Way galaxy, the hundreds of millions or the hundreds of billions of stars that surround us at these large distances. This is a lovely picture taken from New Zealand with a bright light in it, a lighthouse, but still dark skies. So you can see many stars with the naked eye and, of course, more with photography. But modern astronomy relies on huge machines which gather very faint amounts of light from very distant sources. And they span a whole spectrum from nearby objects, which are just very faint, for example, planets going around other stars, or the galaxies, which are so far away from us that they actually are billions of years in the past. It's taken that long for the light to reach us. So we're actually doing we're not only exploring space, but we're exploring time as well. We're exploring space-time with our modern astronomy. Now, this is the VLT, the European Southern Observatory's very large telescope. It has a collecting diameter main mirror of 8 meters. And in fact, there are 4 of them on that mountain, 4 of those big ones. You just see one here. And typically we put these on the top of very high mountains to get above some of the effects of the Earth's atmosphere. This is the summit of Mauna Kea, which is the tallest peak in the Hawaiian Islands in the Pacific. And you see a range of telescopes there. And in fact, the one on the left-hand side, the United Kingdom Infrared Telescope, is where my scientific career started in the 1980s. That's a 4-meter diameter infrared telescope. And I worked on that for my PhD. And that led me, because it's an infrared telescope, it led me to working on what we know today as JWST. Now, that mountain looks great, clear blue skies. And in fact, I've been there many times. It's almost always clear. I was actually married on the summit of that mountain. So that's a kind of a very astronomer geeky thing to do, to get married on top of a tall mountain. But even Mauna Kea has nights when the clouds come. And of course, clouds can obscure your view of the sky very easily. So you can lose time that way. But it's not just that the sky gets covered, but at optical wavelengths and also at infrared wavelengths, the sky actually glows. There is a layer about 80 or 90 kilometers above the Earth's surface where atoms get excited by the sunlight during the daytime. And then at nighttime, they give that energy back. And you see these waves moving across the sky. That makes the sky bright, and it makes it difficult to see things which are very faint. And in fact, this is really bad in the infrared. The sky is really bright in the infrared. And when you go to even longer wavelengths in the infrared, then of course, things are glowing. They're giving out energy. Those of us, wherever you're sitting now, you're probably around 25 to 27, depending if you're in a hot place or a cold place, you're somewhere, in the tens of degrees Celsius. And that means you're actually emitting light at wavelengths around 10 micrometers. So that's 20 times visible wavelengths. So human beings glow, buildings glow, telescopes glow. And for astronomy, that's a bad thing, again, if you want to see faint things. So you want to get to somewhere which is cold, so your telescope isn't glowing. One of the other reasons the Earth is a bad place, now hopefully the movies will work in my presentation this evening, so you can just see this picture of the moon shimmering here, moving around. And that's because of the Earth's atmosphere. Changes in temperature in the Earth's atmosphere lead to these differential motions, things moving around. And that means you can't get very sharp images from the ground because everything's blurring all the time. Now, you can overcome that partly. And in fact, we do this from ground-based telescopes now. We use lasers. We point those lasers into the sky and we make artificial stars, which can then help us correct the images and make the images more stable. So that works, and that works well, but only over usually only very small areas on the sky, small patches. So to improve all of those things, to get above the glow of the Earth, to get above the temperature of the emission of the Earth and the atmosphere and the telescope, to get above what we call seeing, that motion, the best thing to do is to go into space. So this is the Hubble Space Telescope being launched in 1990 on the space shuttle. And I was working on the project at that point. Of course, it was broken when it was first launched. The main mirror wasn't in the right shape. But through astronauts visiting multiple times, we were able to fix it and install new instruments. We have had this magnificent machine now in space for over 32 years, doing amazing science. But as I said before, we know that there is science that can't be done with the Hubble Space Telescope. It's relatively small, just 2.5 meters across. And as I said, back in the 1980s, it was already clear we needed to do more. Now, the other reason we go to space is that the Earth's atmosphere doesn't transmit light at all wavelengths. The light can't get from space at many wavelengths. So what you see here is at invisible wavelengths, that light can get through the atmosphere. That's why we can see the sun, we can see the planets, we can see the stars. But at shorter wavelengths, for example, in the X-ray or gamma ray, or at longer wavelengths in the infrared or all the way out in the radio, that light can't get through the Earth's atmosphere. It's absorbed. And so for that, we need to put telescopes above the atmosphere into space to do those kinds of astronomy. Now, the place which is sort of missing there is between about 1 and 30 micrometers. And that's exactly where James Webb Space Telescope fits in. So some light comes through the atmosphere and some doesn't. But that's a great place for us to go and build a big new telescope. Now, one of the most fundamental images taken by the Hubble Space Telescope is this one. This is what's called the deep field, or in fact, in this case, the ultra deep field. And everything you see in this image, which took about a month to take, so a month's worth of exposures built up and added together from Hubble, everything you see in that image is a galaxy. It's not a star. Each one of those galaxies may have hundreds of billions of stars in. And if you look, you can see some galaxies which are quite big and quite bright, and those are the ones which are quite close to us. But then there are lots of smaller ones which fill out in the background. And those objects are typically further away from us. That's why they're smaller. And also they're fainter because they're further away from us. But I said earlier on, the other point is that because light only travels at 300,000 kilometers per second, it takes time for the light to get to us. So when we're looking at the most distant and the faintest and the smallest galaxies in that picture, we're looking very far back in time, maybe 10, even 11 or 12 billion years. You have to remember that the universe itself is only 13.8 billion years old. We know that from the expansion of the universe, and we can measure the way the universe was when it was very young, just a few 100,000 years after it formed, with telescopes like this. This is the European Space Agency's Planck Observatory, which measured what we call the cosmic microwave background, the glow left over from the birth of the universe 380,000 years after it formed. And all of those lumps and bumps you see there, we know that they have formed into clusters of galaxies in the modern universe. But how do we connect that? How do we connect from those objects to our modern universe when we've never seen the first stars forming? So this is an artist impression of perhaps the first stars forming in our universe. And those stars, if you were next to them at the time, they would have been very bright and giving out most of their energy at optical wavelengths. But because the universe is expanding, that light has actually been moved from optical or visible wavelengths into the red. And this is what we call redshift. When things are moving away from us, like an ambulance moving away from us going down the street, it stretches the sound of the ambulance to lower notes. And the same with light. Light gets stretched out. And so the light which is visible here in our local universe, what we call redshift 0, if we now move to redshift of 3 or redshift of 10, and this is now looking back at the first billion years in our universe, that light has all been moved to the infrared. And so to see those first galaxies and those first stars, we need a very powerful infrared telescope. Not only in the infrared, but it needs to be a big telescope because those objects are so far away from us, they're also much fainter than galaxies nearby. And that's actually what we call a logarithmic scale, factors of 10 on that axis. And so these galaxies at high redshift, the beginning of the universe, are so faint, you need a huge telescope to see them. Now, that's also useful for other things in astronomy. And in fact, more where my scientific interests lie. And that's looking at very cool objects. Our sun is around 6,000 degrees Celsius. And I said before, we in this room, wherever you are in your room listening to this talk, you're at around 300 degrees Kelvin. So a factor of 10 or 20 lower than the sun. And that also puts all the light in the infrared. The cooler an object is, the more of its light comes in the infrared. And in fact, objects at room temperature don't glow in the visible. That's all reflected light when we can see people. But in a dark room with no lights on, you're still glowing at a wavelength of around 10 micrometers. So to see very cool objects, and in particular, young stars when they're being born are very cool. They haven't heated up with nuclear fusion yet. We want to go to the infrared. And the infrared has one more magic trick, which is really important. And that is it can see through dust where young stars are forming. So this is a very famous image from the Hubble Space Telescope, what were called the pillars of creation. These giant structures of gas and dust. And when this picture was taken originally in the mid-1990s, people said, well, somewhere in there are young stars being born. But they really couldn't see those young stars because they're completely surrounded by the dust, which makes that pillar there. But if you go to the infrared, that all just becomes transparent. And the same region at infrared wavelengths from the ground looks like this. And you can actually see at the top of the two brightest or the two biggest pillars, there are now bright sources which weren't there before. And those are young stars being born right at the top of those pillars. So another region which is very famous and people want to look at, and I'm going to be looking at in September with the James Webb Space Telescope, is the Orion Nebula. So this is one of the places nearest to the Earth where young stars are being born today. This is what it looks like with Hubble in the visible. You see the very hot stars in the middle are lighting up this giant nebula. So it glows beautifully in these various colors. And you could see a few other stars in there, but you don't see all of the very young stars, which are cool, and you don't see them also because of the dust. Again, if we go to the infrared, this region changes completely. And we now see thousands of young stars in that same region. And these are only about 1 million years old. So this is very young compared to our sun, which is 4.5 billion years old. So those young stars, I'll be studying those and looking for very, very small ones, which are maybe just the mass of Jupiter or Saturn, but not planets, not going around other stars, just floating freely there. And the other thing I'll be doing with the fantastic precision of the pictures that JWST will deliver is taking images of disks of gas and dust going around those young stars, and that's where planets are being born today. So those dark smudges you see around the young stars there, again with Hubble, show us places where planets are being born today. And when we look in the infrared, we should be able to see some of those planets and see more details in those planet-forming disks. Now, the infrared is a great place also to do chemistry. I don't have any time to describe all of the bits and pieces, but when young stars and planets are being born, there are lots of molecules around. So ammonia and methane and hydrogen cyanide, carbon dioxide, carbon monoxide. And most of the light that they give out when that gas is heated up slightly is in the infrared. So spectroscopy in the infrared, not just taking pictures, but making a spectrum is really important to understand how these things work. And one place that all comes together is looking at exoplanets, planets going around other stars in our universe, mostly in our Milky Way, fairly close to us. But of course, we believe that almost all stars have planets going around them. We can see evidence for those planets, but one thing that the James Webb Space Telescope will be able to do brilliantly is look at their atmospheres and look for molecules which might be indications of possible planets where life could form. We won't see signs of life itself with JWST, but we may be able to see atmospheres where life could be supported. So that's very exciting. So I've given you an introduction to the science. Let's start talking about what we've actually built. So this is the Hubble Space Telescope, built in the 1970s and 80s and finally launched in 1990. It's a 12.5-ton machine with a 2.5-meter main mirror hidden down in the back of the tube. It's about 500 kilometers above the Earth, and actually it's heated by the Earth because it's close to the Earth, and that means that it's not a great infrared telescope. It's glowing at infrared wavelengths, but it's brilliant for visible wavelength astronomy. Now, the James Webb Space Telescope on the same scale has a main mirror 6.5 meters across, and it's a completely different way of building a telescope. You can see the telescope is in the open, and that lets it get cold. It lets it get rid of its energy and put that into the blackness of space. And it's helped by this giant sun shield you see on the other side, which is about the size of a tennis court, 22 meters long. And that sun shield keeps the whole telescope shielded from the light of the sun and the Earth and the moon. And that lets our telescope get to temperatures of minus 233 degrees Celsius, so only 40 Kelvin above absolute zero. And that means that telescope just won't glow in the infrared. It means we can see much fainter objects. And you can see finally, recently I've been able to change that launch date to a real launch date. It did launch on Christmas Day last year, and I'll show you some movies of that a bit later. So this is what the telescope looks like again. There's that big gold mirror, which has 18 individual segments made out of beryllium, a very lightweight mirror. And then underneath it is the sun shield. On the bottom, you see where the spacecraft is, all the warm electronics. And then on the back of the telescope itself is where we have the instruments. And I'll show you some pictures of how the instruments work in a moment. There are 4 main science instruments on the James Webb Space Telescope. So how do we gather light? Well, the first part's quite simple. The light comes in, is reflected from the big main mirror and focused on what we call the secondary mirror. That light then goes in by 2 extra mirrors here. It doesn't go straight to the instruments, but it goes off this mirror. The front one of those, the one on the right, actually can move about once a second or a bit faster in order to keep the images very stable. And that's very important to keep the sharpest possible pictures. That little mirror moves around, making sure we're pointing at exactly the same place all of the time. So a kind of a diagram which shows that the light's coming from the left-hand side is reflected from the main mirror back to the secondary mirror, and then back through those 2 mirrors, the tertiary and the fine steering mirror. And then we get to the instruments. And if you now imagine yourself looking at the sky, the instruments can all look in different places on the sky, and they can all work together. They can all work at once. They can't all look at the same place on the sky, but they can look in different places nearby to each other. And so we can actually maximize the use of the telescope by operating the instruments in parallel. And so we have NIRCam, which is an infrared camera. We have NIRSpec, which is a spectrometer for splitting the light up into a spectrum. We have NIRIS, which is another kind of camera with some very special tricks. And then in the top right corner, we have MIRI, which is a mid-infrared, longer wavelengths camera and spectrometer together. So those are the areas they see on the sky. Well, how do they actually work? So let's start with a simple example. This is the MIRI instrument just as a camera. So this thing is about 1 meter across. The light comes in from the left-hand side here, reflects off one mirror, and then down into the main camera, reflects off another mirror, another one, through a filter wheel, and then finally onto the detector. So by changing the filter, you can take images at different wavelengths. And that's how you, for example, can build up a color picture. You can take images in 3 different wavelengths, and then you will be able to make a full color picture. So that's how you make an image. But what about a spectrum? Well, it gets a bit more complicated when you look at NIRSpec. And that actually allows you to split the light up, not just from one object, from many individual objects. Again, through a filter wheel, reflecting. And now this is a very clever piece of machinery I'll talk about in a moment, goes through that box, then hits a wheel where we have gratings or prisms, if you like, that split the light up into multiple colors. And so it's a much more complicated way of moving the light around, but that now gives us a spectrum for the object we're looking at. But not just one object, can actually look at hundreds of objects simultaneously. That box I mentioned, in that box, we have these units which have little doors on them. Those little doors can open and let the light in from one galaxy or one star, and all the rest will be closed. You can open 100 of those doors and look at 100 objects at once. So that makes the telescope very powerful. And that's, for example, what you would see. This is just a simulation. You see hundreds, or 100 in this case, different objects with different spectra. So you can measure the physics and the chemistry, the temperature, the dust, the molecules and the redshift. You can measure the distance to the galaxy just by looking at its spectrum like this. Now, the other way of taking a spectrum is to actually look at a small patch of the sky and split that small patch of the sky up and get a spectrum for every little pixel in that area. So you get a kind of a 3D cube. You get an image, but an image at every wavelength. And how this works is more or less just magic at this point. So this is the same instrument I showed you first. This is MIRI. The light will be coming in from the right this time, and it will go past the camera into the bottom part of the instrument. And that light then gets split up in some incredibly clever ways so that you can get every pixel gives you a spectrum. And you can see the light is bouncing around all over the place in here at different wavelengths, and then all combining back together to form this. At the end, you will be able to get a cube of image. Every slice of that cube is a different wavelength. And that's going to be a really powerful way of exploring galaxies, for example, and what they're made of and how they're moving. So that's, it's not just taking a picture with these telescopes. We have to do some really clever things with the optics. Now, these have all been simulations. What does the real thing look like? Well, this is to give you a sense of scale. Here are 6 of the 18 mirrors for the James Webb Space Telescope, just about to be tested at incredibly low temperatures to make sure that they are in the right shape. When they were all made, polished, and checked to be in the right shape, they were then assembled into what you see here, which is the full telescope structure at NASA's Goddard Space Flight Center in Maryland. You can see how the big secondary mirror is towering above the primary mirror there. And you can see underneath the carbon fiber structure, which is holding everything very rigidly in place. And here are the 4 instruments. In the top corner, you see MIRI. On the top left corner. The top right corner is near spec, and near spec's bigger. It's about 2 meters in size. And then NIRIS in the bottom left corner, and then the main infrared camera, NIRCam, in the bottom. And in fact, NIRCam is split into 2 halves. It has 2 completely separate camera systems, which are redundant. If one fails, the other one will still work. And that's very important because NIRCam is used to align all of the mirrors in the telescope to make sure they're all pointing in the same direction. And I'll show you that in a few minutes. So we need redundancy in that system. The instruments are then packaged up. This is near spec with all of its wrapping now to keep it very dark inside, being attached onto the side of the module which holds all of the instruments. You can see them some of them in place already. And then that whole system was put into a cryogenic chamber at around minus 233 Celsius again, to test it and make sure all the instruments would work at those really low temperatures. And then the instruments were attached to the back of the mirror. And then the whole telescope in this state, with the primary mirror, the secondary, and the instruments, was put in a big plane, a C-5, and flown across the country to Houston, to the Johnson Space Center, where it was then put into one of the biggest cryovac, so cryogenic vacuum chambers in the world. That chamber was actually built and used to test Apollo modules in the 1960s. So it's the only place big enough, more or less, to fit the James Webb Space Telescope open and able to be tested optically to make sure the mirrors were in the right shape, to make sure we didn't repeat the problems that Hubble had when it was first launched. Now, the thing that's missing from these pictures, of course, is the sun shield, and that was built separately. This sun shield, again, is 5 layers of very thin material, about the thickness of a crisp packet, just very thin metal film. And those 5 layers help reduce the amount of energy falling on one side from about a few hundred kilowatts falling on one side to just a few milliwatts on the other side. And by basically bouncing and reflecting the light back into space. And that allows the telescope then to cool down unaffected by the sun and the earth. Now, that sun shield is too big to be put into a rocket in its full shape. So it had to be carefully packaged up and put all together and then folded around the telescope, as you'll see. I just wanted to point out to Art, and Art's asked me a question: will we be finished by 9 o'clock? I think we will be. I think we'll be done. So Art, you'll be able to go to that. But Art actually worked on this technology more than 25 years ago. So this sun shield is such a critical part of the observatory. Without the sun shield working and then unfolding properly, it was never going to get cold and it's never going to work properly. So here's the full machine as it was on the ground. The main mirror is folded up, and so is the secondary mirror. But you can see the full sun shield, and you can get a sense of the scale now with those people on those cherry pickers. So this is a huge, huge machine. But you remember I said earlier on, Hubble weighs 12.5 tons. This whole machine only weighs 6.5 tons, much lighter than Hubble. So everything on this machine is super high tech, very low mass, and very precisely made, but also has to survive the launch, of course, which was the next stage. So we moved all of this to the European Space Agency's Launch Center. Europe is a full partner in the mission along with Canada. We provided 2 of the scientific instruments. So we have a big stake in this mission, and we provided the launch vehicle, Ariane 5, which you see on the right-hand side and in the middle. And there's the telescope. Again, I showed you that earlier, all folded up and packaged, ready to go on top of the launcher and be launched into space. So now I'm going to drop out of my presentation so I can show you some videos with some sound. So let's just see if that works. StreamYard means I have to share it a different way. So we're going to see 3 movies now with some sound. The first one will be the actual launch, taken by a documentary maker, Sebastian Avila, and he's made a beautiful long documentary you can watch, not just this short section, but this is the critical moment of launch at Kourou on Christmas Day in 2021. And I was there. You can maybe even spot me in some of the pictures. An incredibly exciting moment for everybody involved. So let's have a look at that one first.
5, 4, 3, 2, unité, top.
Decollage liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported. The Ariane 5 rocket continues to fly uphill in nominal fashion.
So kind of the best Christmas a lot of people have ever had. It was quite an amazing moment to be there. And then as the telescope went into space, it then had to actually unfold, leave the top of the rocket, which you'll see in the next screen. And when it did that, it also had to deploy its main solar panel. We had to have power on this telescope very quickly. We only had batteries and we needed power. So let's have a look at that. And it's speeded up a bit here just for the sake, and you'll see a little bit of music as well, showing from the top of the rocket what it looked like when the telescope moved away. That's kind of real science fiction stuff there, seeing that happening. And that was amazing to see on the day, seeing the solar panel opening. I mean, many people were even more excited by that, even than the launch perhaps. And then the third thing we had to do took a lot longer. It took place over a full 2 weeks. And that was actually deploying the various parts of the observatory. So there's a little bit of music here, but I'll see if I can talk you through that as well. It's a very complicated process to unfold this observatory. So the first thing you'll see is that unfolding of the solar panel there that happened just a few minutes after launch. And then things started happening much more slowly. The high gain antenna to bring data back to Earth. And then the folding down of the sun shield happened gradually over a few days. And the telescope was lifted away from the spacecraft in order to get so that it could start cooling down and not be connected so strongly to the spacecraft. We deployed this tab at the back, which helps us balance the telescope in space. And then we actually rolled back the covers and started pulling out the sun shield. This was slow. It took days. layer by layer, pulling out and tightening up into the final shape, which you'll see in a moment. And this all involves cables and motors and different deployment mechanisms and pulleys. Really, really scary. Never done at this scale in space before. And for many of us, this was the thing that was most likely to fail, or we thought it might. But it didn't. It deployed perfectly. And then we deployed the secondary mirror over the back. And you'll see at the back of the telescope now a radiator lifting up so that the instruments can get cold. And then finally, the main mirror deploys around to form the full shape. So I'm going to go back to the presentation now, and we'll finish off in the next 10 minutes or so. And then we'll leave room for questions, of course, because I'm sure that's people have got interesting things to ask. So, okay. Let's see what's going on here. So at the same time as we're unfolding the telescope, we're traveling out to a place called L2. This location is 1.5 million kilometers away from Earth, and is a place where you can orbit with the Earth, but always keep the Earth on one side of the telescope, the Earth and the sun, and that lets you hide the whole telescope behind the sun shield. That lets the telescope get very cold and allows us to be a sensitive infrared observatory. So you can see it's not staying at L2 at a point, but it's orbiting around it every 6 months or so. And that orbit looks like this. It's quite a big orbit. It's about 800,000 kilometers across in radius. So it's a huge orbit. But it, as I say, the main thing is it keeps the sun and the Earth in the same direction the whole time. And that then allows us to get cold. We can observe different parts of the sky by rotating the telescope around the axis connecting to the sun. So we can take a kind of an annulus in the sky all at the same time. And then during the year, as the telescope moves around the sun, we can look at all places on the sky. So we will be able to look at all places as long as it's outside the Earth. We can never look towards Mercury or Venus or the sun itself. But we can look anywhere else in the universe just over a period of a year. So one of the first things that was then done was to pull those 18 segments of the primary mirror, to pull them together. So we had to find them first. Where were the different parts of the mirrors pointing at launch? We were able to find them and then move them into this shape here to start then focusing those individual segments. And you'll see that the image is getting sharp here. So we're able to individually align and focus all of the mirrors. And then we could move the images, the 18 images together to just make one stacked image. So you're just seeing one star instead of 18. And then we were able to what we call phase the mirrors, move them by very small amounts so that they're all exactly the same distance from the star we're looking at. And that allows us to get even sharper images. And this is the famous first image, which was seen from James Webb Space Telescope back in March. It's superbly sharp. It's an amazing picture. The big spikes you see there come from the hexagonal mirror, as you might expect, in fact, completely as calculated. And if we then blow up the image just in terms of the color, we can see that all over the background there are faint galaxies. And so this is just a test image, just engineering, but it allows us to begin to see how this amazing machine works. For the last few months, we've been aligning everything and testing. And recently we looked at a place in the Large Magellanic Cloud, a nearby galaxy. That's where all the instruments are. So this is the image you saw before of how the instruments look. And now with real data instead, here are all the instruments looking at space, gathering data, superbly sharp images across all of the images. And if we zoom in a bit, you can see how crisp the images at the bottom are there. And the one in the top right corner, Miri, looks a bit fuzzier because it's actually at much longer wavelengths. You get less resolution at longer wavelengths. But just to show you how much things have improved between the previous generation of mission, Spitzer, and Miri on James Webb Space Telescope. Just have a look at this little movie here. That's Spitzer. That's the same place with the James Webb Space Telescope. We'll jump back to Spitzer. That's what we used to be able to do. And this is what we can do now. So these are remarkable pictures. And these are all engineering images at this point. We've nearly finished commissioning the telescope, which means checking all the instrument modes out, making all the different ways we can take data, make sure they all work. And you can see roughly half of them are crossed off already, and you can follow that day by day on that website. Another one has been crossed off today. So we're now really close to finishing. And in fact, some of the first science observations are being taken right now. And the first images, the first full images and science data will be released on the 12th of July. So just 3 weeks from now. So it's a really exciting moment for me to talk to you about the mission. What's coming next will be exciting, and what comes after that will be even more exciting. The one thing I didn't say in all of this is that originally we hoped that we would have at least 5 years of lifetime for this mission. We thought we would have 10 with the amount of fuel we had on board, but we saved so much fuel on the launch because the Ariane 5 was so precise in putting us on the trajectory to L2 that we were able to save enough fuel that we believe we now have 20 years of lifetime for this mission. So the kinds of science you're going to start seeing very soon are looking in our solar system, looking at the planets beyond Earth, Mars, Jupiter, Saturn, comets, asteroids, things out in the Kuiper belt, faint fuzzy objects, things like 67P Churyumov-Gerasimenko, objects filling our solar system. We'll be able to look at them with amazing precision in the infrared. We'll be able to look in places where planets are forming around other stars, like in this impression here. We'll be able to look at some of those planets in their atmospheres themselves and see if they're places which might be suitable for life, or maybe not. Maybe they're very strange planets that form completely differently to our solar system. We'll be looking in places where young stars are being born in huge clusters of tens of thousands of stars, looking through that dust again and looking at those cool objects. And then looking further out, we'll be looking into the rest of the universe, looking at galaxies and how they change over time, looking at how they collide, look at how stars are triggered and form when galaxies collide. And then looking even further, deeper back to when the first galaxies were made, how does material flow together down the web, the filaments of dark matter, to form the first galaxies in simulations like this. And then right at the outer edge, going all the way back to the beginning of time, looking for those very first objects that formed in our universe, maybe 13.5 or 13.6 billion years ago, taking a picture like this is a Hubble image again, but going much deeper, seeing things further back in time, a cosmic journey all the way back to our own origins. And I'll finish with one last slide. This is not only a cosmic journey for the telescope and for scientists, but even for those of us who worked on it. Many people have been involved in this project for a very long time. So my cosmic journey has taken me 23 years, 24 years now, from when I started in 1998 with the European Space Agency as an outside scientist. Then I came to ESA in 2009. 2021, I was able to see the telescope that we had worked on for so long and saw it go into space. And this is just the beginning. This is just the beginning of an astonishing adventure. We don't know what the future will hold, but we do know that it will be amazing because of what JWST will do. And the last thing to say, this is your telescope. You paid for it, and we'll be taking data with it, but you could apply for it as well. Maybe there are students watching on today, somewhere in the next 10, 20 years, you'll be using this telescope as well to explore the universe. So with that, I say thank you and dziękuję.
Thank you very much. I would like to give a floor to Arthur because he has to go very quickly because of a very important meeting. It was very fascinating presentation. So Arthur, last word for you, and then I will give questions from our audience to Mark. Thank you.
Okay.
So do you have questions from the audience? In the meantime, maybe you could see what questions the audience has. But there were, one of the questions is, you show these beautiful colors from James Webb or beautiful pictures from space. And people always wonder if these are true colors or these are adjusted to make it pretty. And what does it mean, a true color? You know, true color eye sees. So can you comment on this?
Yeah. So when we take pictures with Hubble, for example, it is possible to take pictures which are red, green, and blue, and that's what your iPhone or any webcam does. It doesn't actually take a color picture. It takes 3 black and white pictures with different detectors, different filters, and then puts them together to make an image like we would see. So this picture you're seeing of me now, I mean, it's mostly true color. This is more or less what I look like. But with telescopes like Hubble, you can use other filters. You can use a filter which concentrates on very narrow parts of the wavelength spectrum. For example, one molecule or one atom emitting. But you can call that the red image. And then you can take a picture through another filter, which might be another line, and call that the green one and the blue one. So we will put those together and make a color picture. And in many cases, they are not what the human eye would see. But we say they're true color because they are colors that mean something. They're not just kind of painting everything reds and blues artificially. If something is, in one of these images, if something is bluer, we can say, oh, it has more of that gas in. If it's redder, it has more of that gas. So it allows us to use the color as a way of looking to do physics. Now, when we look at infrared with JWST, well, humans can't see in the infrared. So all of the wavelengths we'll be looking at in the infrared are not visible to humans. Snakes could see things in the infrared. They're quite good at that. And some insects. But for humans, everything that you see from JWST will not be something a human could see. But the colors you will see, they are meaningful. They will be colors which tell us something about the physics. We will have put 3 different images together in 3 different wavelengths. And we'll say, there are hot objects and there are cold objects. There are dusty objects and there are objects with lots of hydrogen around them. So for us, that will be very meaningful physics. But it's always a good question. I mean, and the other thing you have to remember is that humans only have quite small eyes. We can't see colors very well in the night sky because we don't collect enough light. Things which are very faint, normally we actually take pictures which are very long, maybe minutes or hours or even weeks long, to collect enough light to be able to see color in the first place. So in that sense, if human beings went into space, you would not see much color at all, I'm afraid. Space is quite faint. Even if you went next to the Orion Nebula, the picture I showed you on, you say, oh, it'd be great. I want to go to the Orion Nebula and see it in color. It would look gray because it would still be incredibly faint and you would not be able to see any colors. So please don't plan your holidays to go to the Orion Nebula. It won't be exciting. Just let us take pictures of it for you from here.
Okay, thank you very much. Arthur disappeared once more time, but yeah. You can see that he took a picture, so he's ready to share it on internet. Oh, Arthur, you are disappearing all the time, so I would like to thank you very much for being with us. I know that it's not our last meeting in We Innovators Club, and also personally, I hope it's not our last meeting. Thank you very much. It was great pleasure for us. And I know you have to go to make space business in the US. So thank you.
Thanks very much, Art. I look forward to seeing you again in person soon.
Yeah, nice to see you again, Mark. You're an amazing guy. You work on astrophysics, astronomy, planetary, heliophysics. I only deal with planetary, just tiny portion of it. And at that, I'm looking now only at Mars and Venus. So, I'm just 1% of you.
Those are cool places. Those are cool places. And we'll join you there. And next time you're over, I do something else as well. You should have to come and join us at one of our rock gigs that we do with musicians and artists and science fiction people. That'd be cool to have you involved.
Okay, guys, don't say things like that.
Thank you, Mark. Thank you, Bartosz. Thank you for inviting me.
Thank you. Bye-bye. Bye-bye.
Thanks, Art. Bye.
See you. Okay, Mark, I will go to next questions from our audience.
Yeah, sure.
I think it's not more than 10 minutes now.
So however long you like, yeah.
Okay, so a question from Milena. What about data reduction? Is it carried out at the spacecraft? In which form data is transmitted to the Earth?
That's a great question. We're at L2, and that's 1.5 million kilometers away. So it's kind of difficult to get back lots and lots of data. We had kind of data limited to about 20 gigabytes a day, if I recall correctly. So, you know, I have a little hard drive I just plugged into my laptop a couple of days ago. It's got 4 terabytes on it. But we can get about 20 gigabytes a day back. And that means we can run all of the instruments. We can take plenty of data with the instruments, but we can't necessarily run them all at full speed all the time, for example. So we have to be a bit careful. But basically, all of the data is sent back to Earth. We don't do data reduction on board. We store the data on board and then we send it back to Earth. And the reason for that is that there are some very clever tricks we can play with the data. And those tricks will probably change as we get used to how the data look in space. One thing that's really important in space is particles, cosmic ray particles hitting the detectors and kind of making hot pixels. And we have ways of getting rid of that with clever processing. But we will have to learn how to do that properly when we see the data from James Webb. So if we were doing that on board, we might have the wrong algorithm. So it's better to send all the data back. Now, this phrase data reduction is a weird one as well, because the last thing that ever happens with data is that you reduce it. You make more and more and more. Every step you produce new files and new versions of the data. So data just expands all the time. But this, of course, will be a huge piece of the work that everybody will be doing. And it's a new telescope. So people will be learning for the first time in the next weeks and months how to analyze the data. And in fact, one of the things we're doing on the telescope is putting a lot of data in the public domain straight away with no delay. So that will start on the 12th of July. And other scientific data for scientific projects will be fully available to all astronomers in the world, everybody, not just the United States, Canada, and Europe. And that will mean people can start playing with the data and experimenting with it. And then they will be better able to work out how to write their own telescope proposals. Because the next deadline for applying for time on Hubble, you write a proposal, it gets compared to all the others. It's competitive, maybe 5 to 1 or 10 to 1 chance. The next deadline is at the end of this year or the beginning of next year. So it'll be very soon that people will have to write to put in proposals. So that's why the data will be coming out. So anybody who's interested in astronomy and wants to use JWST should be playing with the data very soon.
Okay, thank you very much. Next question from Janusz. How collision with space particles will influence quality of operations?
Yeah, you probably know we're at this place L2. We're not going to get hit by other spacecraft. We're not danger from debris and other satellites because, like you are in low Earth orbit. But even out at this L2 point, there are bits of dust flying around, pieces of comets, pieces of asteroids, which are just, high-speed dust particles, maybe very small, but because they're moving fast, they can cause damage. So we know we've been hit a few times on JWST already by these dust particles. There's no surprise. We have had other spacecraft there. We know this happens. We did have quite a big hit on the telescope in May. And that actually hit one of the mirrors, one of the 18 mirrors, and we could see it in the data the next day. We could see that it had affected the data, but not so much that it actually changes the performance of the telescope. Actually, the telescope is better than we designed it in the way that everything's lined up, or better than we hoped for. So even with this hit on this one mirror, the performance is still better than hoped for. And if you think about it, even if we destroyed one of the 18 mirrors with a huge thing hitting it, it's just one of 18. So we have ways of correcting for these things as well, slightly changing the shape of the mirror if you get hit by something. And also when there's a meteor storm, we can turn sideways and have the meteors go sideways past us. So it is something which is folded in to our prediction of the lifetime of the observatory and how good the quality will be. We knew this would happen before we went. So there's nothing to be worried about, but yes, it will happen. And Our other satellites out there, like Gaia, we see hits from dust particles. We can measure them. We know what they look like, how fast they're moving. And yes, it is one of the features of putting a telescope in space. There's no doubt.
Okay, thank you. Now my question. We know that everything is getting smaller from year to year. And how do you think, what size the Webb telescope was today?
Well, it's the size it needs to be in a way. Size counts in astronomy. The bigger a telescope gets, the more light it can collect. You can't make a telescope smaller in that regard. And also the resolution, the detail that you can see in images with a telescope is directly proportional to the size of the telescope. So if you double the size, you get twice as much detail. And we knew that we wanted the kind of resolution that a 6.5 meter telescope would deliver. Of course, you want more. So maybe the next generation will be bigger, but they won't be smaller. Not if you're building a full observatory like JWST. There are other missions which you can say, well, actually, I don't care about image detail. I just care about observing lots of objects across the whole sky. So, for example, our Euclid mission has a smaller telescope, but it has much bigger detectors, and it will see more of the sky to look for dark energy and dark matter. So you need to choose what the science you're doing. On the ground, we're already building telescopes with mirrors almost 40 meters across. And that's, again, to get much more resolution and collecting area to see faint objects. There are clever ways that we can combine light, which maybe we would change the technology in some parts of JWST, but not the main mirror. Size counts. It's really important.
Okay. Next question from Milena. As for the Spitzer and JWST comparison, one thing is more sophisticated instruments or JWST. Other thing is the size of the mirror. How much does the diameter of the mirror affect to this comparison?
Well, in the pictures you saw, the resolution difference is all down to the size of the mirror. I think Spitzer has a small mirror, about 40 centimeters, JWST 6.5 meters. So that gives you immediately a factor of 15 better detail that you can see. The instruments is an important point. The instruments on JWST are very complicated, very sophisticated, allow us to do lots of different kinds of science. Spitzer was a great mission and it did amazing science, but it was done, it's finished already. It was built earlier. It was also looking at longer wavelengths than JWST. So it was a complementary mission and coming earlier. The instruments have, clearly will have lots of complicated ways of taking data, and that means the data reduction will be more complicated for JWST. So again, it's similar because it's a cold telescope and it's an infrared telescope, but more or less everything is different. It's a much bigger telescope and has much more complicated instrumentation than Spitzer. But again, nothing, Spitzer was great, Herschel was great, ISO were great, the previous infrared missions. And without those, we wouldn't have the mission we have today.
Okay. And the question from student. Mark,
Sure.
Do you have any advice for students starting the scientific careers?
Well, yeah, look, it's a really exciting time. Particularly as James Webb will be here. And in fact, those of us who are using it today, who are lucky enough to be, right there now, we probably won't be doing the most exciting science in some ways. It'll be the new people coming along who will have learned how this machine works. It was true with Hubble. Hubble was never designed, for example, to look at exoplanets. But some of the most exciting results coming from that mission in recent years have been in that field. So I think it's a really exciting time to come into the field. And it's not just James Webb Space Telescope. Next year, we'll be launching a mission to Jupiter called JUICE. As I said before, we are arriving at Mercury in 2025. We're building new missions for dark energy and dark matter, big new X-ray telescopes and gravitational waves, amazingly important things which were discovered just a few years ago. We predicted they must exist, and we've seen them now, but we're doing a big gravitational wave observatory in space called LISA. Amazing technology, amazing precision, measuring the shaking of space-time as black holes combine together. So there's a huge range of things. Plus, we're going to Mars to bring samples back to Earth. Art was just talking about that. There's a lot going on, and big telescopes on the ground as well. So there's a lot to do in observational astronomy and planetary physics. We also need theoreticians, we need chemists, we need lab physicists. So there's a huge amount going on. I would recommend that you get involved.
Okay, and question from Adam. It's good that you mentioned Hubble, because the question is, how is Hubble and Webb now being used?
Yeah, so Hubble is still,
yes.
yeah, Hubble is still being used. Hubble has good instruments on board. It has a finite lifetime because it's in low Earth orbit, and it will slowly drift down towards the Earth. And some of the systems have failed over the years, as you know. We've replaced them by astronauts going there, but there are no more astronaut repair missions planned. So we think Hubble and JWST will overlap for some years. But in the end, the one thing we have to be careful with Hubble actually can't be, it doesn't have any rocket motors on board. We can't take it out of orbit in a controlled place. And that means it could be dangerous if it hits on land somewhere, for example. Now, the chances are it will go in the ocean because there's more ocean on the Earth than there is land. But what there probably will have to be at the end of life for Hubble is a deliberate deorbiting mission. So going up to it with a robot, attaching a small rocket motor and actually putting it into the South Pacific to avoid hitting anybody. Now, my personal preference is actually, if you've got a rocket motor, push it up to 1,000 kilometers and leave it there for somebody to pick up in a museum 100 years or 1,000 years from now. It's not so easy, but you know, I think Hubble's earned a place in a museum somewhere in the future, not a grave in the South Pacific. But I'm not paying for it, so I don't get to decide.
Okay, and our last question, again from Shimon. JWST project took very long time prior to launch. Were there some parts of the hardware that were redesigned number of times just because of technological development in the meantime?
Not really. I mean, if you look at what we had to do for the James Webb Space Telescope when we started, really we started around 2000. There had been lots of work done from the 80s and 90s to get ready, but we knew we had to develop a number of new technologies. So the mirrors, the sun shield, detectors, a cryo cooler for the instrument. The MIRI instrument is actually cooled with a special cooler. The other instruments are just cold because they're in this cold place in space. There are a number of technologies on board which had to be developed, and that's really where a lot of the time was spent. So we didn't kind of come back and say, oh, well, we've built that, now let's just get new things. We were building the state-of-the-art technologies along the way. And in fact, some of them didn't fully work, so we did have to go and re-engineer them, but we didn't kind of throw them away and start from scratch. Most of the technology development, you know, what do? Do you build mirrors out of beryllium or out of very thin glass, out of other metals or other glass? That was done back in the 90s and the early 2000s. Once we started building it, the design stayed pretty much the way it was supposed to be. You might have slightly better detectors today, for example, but the JWST detectors are the best in the world in the infrared. Nobody else makes them the way we have for this telescope. So I don't think, you know, it's not like your iPhone where it changes every year. The technologies we're developing are for very difficult environment, very complicated. They're very special, non-consumer technologies. So there aren't too many other people that want to buy them either, if you like. And that's what, of course, drives the market, innovation market in consumer goods, is that things change every year because there's lots of money being spent on technology. With missions like JWST, it tends to be very specific to what we're doing in space. But I think we have the best technologies available today on that telescope. There's nothing really that I would go and change. Maybe the size of the computer memory. Maybe you could double that, for example, but it still has to work in a very crazy environment with lots of radiation. My 4 terabyte hard drive wouldn't be great on JWST. It would not store the data properly.
Okay, Mark, thank you very much. It was a great trip with you.
Thank you.
Thank you very much for showing us and our audience your experiences. It was really, really exciting. Great presentation. Maybe one more question. What is your dream for next 1-2 years? in space
Well,
and in real life? And
yeah, it's a good question. I mean, the things I proposed to do 20 years ago have still, nobody has been able to do them. So we need JWST. And the first data start coming in September for my projects. That's when I can see Orion and other places in the sky. So that's going to be a very exciting moment after so long working on the mission. As I said briefly at the end of my presentation there, we're doing other things which are very interesting, working on outreach, working with musicians and artists, trying to bring scientists and engineers, astronauts together with poets and painters and filmmakers and actors. And I think that's something which is a big focus for me as well, this public outreach, making sure that people see what we do, not just as astronomy or not just as technology, but as part of civilization, as part of culture. The inspiration that looking at space can bring is not only important for scientists, but it gives a bit of perspective about what it means to be human. And I without getting political, I think we could all do with a bit more perspective on what it means to be human. Very short-lived in a very complicated universe, and perhaps we should be a bit nicer to each other. We're not doing really well at that at the moment. As I say, I don't want to get too political, but I come from a country that's falling apart, frankly. There we have problems in Europe. We have problems with the climate change as well, huge issue. And if space can bring people into science, because these lovely pictures and this technology, if you can bring them into science and innovation and help solve the huge challenges we have on this planet, whether it's technology or politics or the culture, we should all be talking to each other much more and realizing how fragile life is.
okay, thank you very much. So I would like to ask Pavel to invite everybody of you for our next meeting next week.
Yeah.
Pavel, who will be our guest?
I don't know if our great I don't know if our great audience know this, but this year we are celebrating 10 years of Poland membership in ESA, and it was a very important time for Polish space sector. So on this occasion, next week we will meet Josef Aschbacher, Director General of European Space Agency. Where we know this 10 years. The host of this meeting will be probably known to you, Rafał Modrzewski, CEO at ISI, and the president of the Polish Space Agency, Professor Grzegorz Wrochna, will also take part in this discussion. So we cordially invite you to this meeting.
Thank you very much. Have a good night, and think all the time about space, about we innovators. Thank you, Mark.
Thank you.
My pleasure. Thank you very much, both. Thank you, everybody. Bye-bye.
Bye.